Here you can see a pendulum containing 3 different bodies. This is a physical simulation, and let's see what will happen if I start the simulation. You see, this is a very chaotic behavior, and it's not easy to predict just by looking at it where the blue part of the pendulum will be in the near future. In this video, I will introduce you to a very simple or to a basic method which allows you to actually compute the movement of such a pendulum and other physical systems. Hi, my name is Frank and welcome on my channel. In this video, I will introduce you to the explicit Euler method, which is a very basic and a very simple scheme to numerically solve ordinary differential equations. What you should already know is you should have some basic understanding of analysis, and you should have seen an ordinary differential equation before. So you should know how it looks like, how it works, and it's good to know how to actually model, how to use them to model physical systems. And in addition, it's always nice to have some basic understanding of numeric mathematics. So what's the aim of this video? In this video, we are gonna talk about initial value problems like this, which contains of an ordinary differential equation. So y prime is f applied to y with a function f. And in addition, we have an initial value. So at time t0, our function y should equal to y0. I'm not bothering, or in this video, I'm not bothering about how to actually analytically solve this problem. In this video, I will talk about how to use the computer to solve this method. So how can an algorithm look like to solve this problem? We'll have some standing assumptions throughout this video. We assume that the initial value problem I just presented to you actually is uniquely solvable. This is a very strong assumption, but luckily we can use the famous Picard-Lindelöf theorem, which actually gives us exactly what we'll need. So let's look at this theorem in a bit more in detail. We have a continuous function, and it should satisfy the Lipschitz condition on the second argument. So it's a one-sided Lipschitz condition. So in the second argument, so you and me should this equation, this inequality should hold with some constant L. It's important that this condition inequality should hold for all t simultaneously, and our upper bound L is independent of t. If this is satisfied, then we know that the initial value problem, which you can see here, has exactly one solution. That is a very nice theorem, and it gives us the knowledge that we actually have a solution, and in addition, it is unique. To check on this condition, you do not have to check on this Lipschitz condition by hand. You can rather use the more strongly condition here. We know the Lipschitz condition is satisfied if f is continuously differentiable and the partial derivative of f with respect to the second argument is bounded on the interval we are looking at. Of course, just apply some mean value theorem and you actually just end up with this inequality here. So this is a very nice trick to actually check on the uniqueness of initial value problems, to check is this continuously differentiable and the partial derivative is bounded. There you go, apply Picard-Lindelöf and you're done. So how can an algorithm look like to compute the solution to the initial value problem? Well, we start with the fundamental theorem of calculus, which puts the antiderivative and the continuous function small f and big F into relation. Well, everybody knows the fundamental theorem of calculus, which basically says the integral over small f is big F evaluated at the upper bound minus f evaluated at the lower bound. How does this help us to solve the initial value problem? Well, we just have here our ordinary differential equation, and together with the initial value, we have our initial value problem. And we just integrate them. Well, we start here. So we integrate over y prime from t0 to t. Using the fundamental theorem of calculus, we achieve the left-hand side, which is just yt minus yt0, which is, well, by definition, here we have the definition of the initial value, which is just y0. On the other hand, we can use the ODE, and we know y prime is f evaluated at y. So we have reformulated our initial value problem using a fundamental theory of calculus, and we achieve this so-called integral form of the ordinary differential equation, or to be more precise, of the initial value problem. And this is nice because now we can actually approximate the integral here and get an approximation for y of t. This is exactly what we're going to do now. So here we have a nice smooth function called f of x, and we want to approximate the integral of f from a to b. So let's add some values a and b. And what we're going to do now is we add a horizontal line at the value of f of a. So here we have f of a. What we're going to say now is, okay, we have this red rectangular. This area is something we can compute. This is just b minus a times f of a. And we say, okay, well, this is good enough for us. So the dotted area is the integral we want to approximate. So this is f of s from a to b. And we say, okay, well, b minus a times f of a, so the red area, is good enough for our purpose. Just a small remark here. If you are familiar with the Riemann integration, this is exactly what you're going to do here to get the so-called left-handed Riemann sum. We now use this approximation to establish our algorithm. First of all, let's introduce a t1, which should be bigger than t0, and the difference of t1 minus t0 is called h. And we find y0 to be y evaluated at t1. So we use now our integral formulation to get the value of y at t1, which is just y0, plus the integral over f applied to y. And we now approximate this integral using the approximation we just established. And well, we end up upper bound minus lower bound, t1 minus t0, which is just h, evaluated at the lower bound, and f evaluated at the lower bound, which is just f evaluated at y applied to t0. So, but we know y of t0, this is just y0. So finally, we'll end up with an approximation of y1. So y1 is just y0, and it's this value here, plus h times f applied to y0. These are all values we already know, because of y0 we are starting with. H is given, so we now have a formula to compute y1. This is an approximation of y applied to t1. And we can move this a little bit further. So let us now discretize the whole time interval, which is from t0 to bar t, into equidistant intervals. So t1 is less than t1 is less than t1, and so on, such that all neighboring t's have the same distance. So tj plus 1 minus tj should be h with some fixed h. And now we can repeat this approximation and get that yi plus 1 is just the preceding value, so yi plus h times f evaluated at yi. This is a nice recursive iteration, which we can use to solve our initial value problem. So what is happening here? An alternative approach to derive this formula is to apply the Taylor formula, which might give some more insight into the logic what is happening here. So let's Taylor y at the position at the point tk plus 1. Well, just apply Taylor. This is approximately, if the distance here is not too big, this is y applied to tk plus y prime at tk times the difference. But the difference tk plus 1 minus tk is exactly h. And we can now replace y prime tk using using our ordinary differential equation, y prime evaluated at tk is just f applied evaluated at y tk. And this is exactly our formula, which we have derived using the integral approximation. This is just a different approximation. If we use the approach of the Taylor approximation to derive our formula, we can plot some nice graphs, some nice visualization of what actually is happening here. So let's assume that this blue function here is our solution to our initial value problem, which is given by yt. And the x-axis is the time we want to integrate along. So at time t0, we are on this graph, exactly on this graph at this point. And now we just apply our formula. So we add to y0 h multiplied plus the derivative of y. So we might end up at a point here, which is given by t1 and y1. So we see we are leaving the actual solution and kind of get an approximation. However, this approximation error you can see here will increase over time because we are now starting at a point which is not on the solution, but rather a little bit off the solution. So we now repeat our iteration, our formula, and we end up with y2, which again is not on the solution, but it's an approximation. And we now continue this and we see the error might be increasing. So the distance of y3 to the actual solution might be bigger than here. So we have an increasing error over time. And this might cause some issues which you will see later on. So you see, we get an approximation of the real solution. So we can extend this solution and this method to systems quite easily. Just repeat the whole derivation, and you will see there's no big difference if you work with systems. So you end up with the same formula. The only difference is that y is a vector and f is also a vector. That's the main difference. But that's all we need to take into account here. Let's take a look at a more complex initial value problem, which consists of two coupled ordinary differential equations, x for x and y. And I made here a small change of notation. For the time derivative, instead of x prime, I use x dot, which is the physical notation, just to inform you. Which you might see quite often. So let's take a look at this equation. We have two coupled equations. And we have initial value. So at x0, we want the value to be 1 and y at 0 to be 0. If you take a little bit closer to the problem, you see that the solution is given by cosinus and sinus. Just plug it in here. This term here will drop out because we are all staying on the unit circle, and we just end up with this here. This is a quite interesting test problem because if we start with this initial value here, we can actually see the impact of the discretization quite a lot. So let's take a look at the solution in the phase diagram. So the phase diagram is nothing special. It's just f plotted as a vector plot, which actually is the gradient of y, because this is our ordinary differential equation. So we have three different discretization parameters. So this is the biggest one, this is the intermediate one, and on the right hand side you see the smallest one. For the time equals 1, we see they all look the same. Nothing changes for t equals 0, so we're still staying on the unit circle, which is around here. No changes for t equals 3. But now you might see some issues, some small difference for t equals 4. You can see here, this line is not in sync with this here and this here. And if you go to t equals 5, you see, okay, the solution is now looking completely different for the small discretization parameter. And for the biggest small discretization error. This is exactly what I showed you in the picture before. Due to the discretization error, we might leave the solution completely and run into some numerical errors. Let's compute this for t equals 6. And again, for the intermediate solution, we are also leaving the unit circle and kind of getting to infinity. And here, for the biggest parameter, we are far away from the actual solution. For the smallest parameter, things are actually looking quite good. We're still on the unit circle. And finally, if we do this for t equals 7, well, for the biggest discretization parameter, the solution is off to infinity. It's also going to infinity for the intermediate parameter. And again, for the smallest discretization parameter, it's still looking good. So I'm sparing you the details of the conversion analysis, but you can guess the smaller discretization parameter, the better the solution. I promised you in the introduction that we are going to deal with the pendulum, and I promised that we can calculate the behavior of such a model. But before we can actually compute this, we have to do some physical modeling and some calculations. So here you can see a pendulum consisting only of two bodies connected with a joint here. This joint has the first body has length L1 and the mass M1, which is located here, and similar for the second body. And what we're gonna do now, we're now putting up a system for the angular θ1 and θ2, which allows us to calculate the position of these two knots here and to plot it. So keep this picture in mind. This is what we're gonna do. So this is the discretization, the description of the parameters we're going to use now in the next slides. We have to do some Euler-Lagrange formalism to get the equation of motions. I'm sparing you the details. It's not that complicated. It's just a huge pile of derivatives and calculations. They look like this. In red, I marked the angular, and you see the first and the second derivative of the angulars are popping up. So these are our parameters, our variables we are going to compute. But with this system, we can do nothing. It's not in our formula, not in our formalism. We need to apply our method. So we have to do some rearrangement. So let's go quickly through it. You can redo the calculations if you want to. First of all, we rearrange the equations in such a way that they look like this. So we bring all terms on the right-hand side, call them F1 and F2, which consists only the first derivatives or even no derivatives. And on the other side, we sort them with θ1 double prime and θ2 double prime. And if you do this, you'll end up with something like this. Here you have the details. They're not so important. It's just rearranging equations. But this thing looks much more nicer. What we're going to do now is we bring this into, first of all, we drop the arguments because nobody needs them and they're just disturbing. And we are bringing them into a matrix form. So they look like something like this. We now have to check whether the matrix is invertible or not, but in fact it is. You can check it if you want to. So this allows us to invert the matrix and bring the matrix to the other side. Why are we doing this? Because we now have isolated the second derivatives of the angular θ1 and θ2. So an equation looks like this. I'm just rushing through it because it's technical details. It's not that important. Just multiply this matrix vector multiplication and call the resulting components G1 and G2. They look like this. Just do the calculations. And we're still very close to our formalism, which we need to apply our method. But we still have here some second derivatives popping around and we don't want them. So this is now what we're going to do now is a standard trick. Well, to get rid of the second order derivatives, we introduce additional variables and call them omega 1 and omega 2. So omega 1 is just theta 1 prime and omega 2 is theta 2 prime. So these are the missing first order derivatives. And if we transform the system into a system containing only first order derivatives just by adding these two additional variables, we end up with this super nice equation here. So on the left hand side, we only have equations here with the first order derivatives of theta 1, theta 2, omega 1 and omega 2. And we call this vector y. And on the right hand side, we end up with, well, whatever stands on the right hand side. And this is perfectly for our setting, because now we can apply the Euler method to solve the system. Of course, we have to do some reformulation to get the actual position in the Cartesian system, but this is just a standard. If we know the angular theta 1 and theta 2, we can compute the position in the Cartesian space. Here you can see now 3 different calculations for the pendulum. They all start at the same initial position, but we vary the discretization parameter from 0.01 to 0.0025. And let's see how the discretization, which impact does the discretization have on the calculation. You can see that after a while, the 3 different calculations, they go into completely different directions. This is due to the discretization parameter, as we mentioned before. These are the final position at time 20 for the 3 different calculations, and you can see, well, they look completely different. And this is actually what we expected from our discretization parameter. We now have arrived at the end of this video. Let's draw a small conclusion. So I showed you how to derive the Euler method, which is a very simple and straightforward method to solve ordinary differential equations. It's very easy to implement. It's just basically a couple of lines. And it was based on approximation of an integral. I want to close this video with a small remark. If you choose a different approximation rule for the integral instead of the very simple left-handed box integration approximation we have done, this of course leads to different algorithms. They are either more complex or more stable or have better convergence properties. We haven't talked about the stability and then convergence in this video because this is way too far to put it in YouTube videos. If you're interested in this, just open Google and plug in stability properties of Euler method or something like this, and you'll get a bunch of informations. I hope you'd enjoy this video as much as I have enjoyed it making it. And see you around, have fun, and take care.